Welcome to our breakdown of Chapter 3, Properties of Solutions, by Michael E. Alton. Today, we are exploring the physical chemistry of dosage forms. Solutions can exist in multiple phases, but in pharmaceutical science, we are almost entirely dealing with solid solutes dissolved into liquid solvents. The core challenge is tracking what happens to the physical properties of both components once that solid crystal disappears into the liquid medium. Measuring these physical shifts is the mandatory first step before we can engineer any effective delivery system for a drug. Under the kinetic theory of matter, molecules in a solid crystal lattice are locked in place. As thermal energy increases, these molecules begin vibrating, eventually overcoming the intermolecular forces holding them together to form a cohering fluid-liquid state. The intermolecular bonds in a solid are incredibly strong. Because the bonds in liquids are looser, it is far more common for molecules at the surface of a liquid to escape as vapor through evaporation, compared to the rare process of a solid sublimating. When we dissolve a solute into that liquid, molecules of both components compete at the surface. Their relative tendency to escape into the air dictates the total vapor pressure of the solution. Pharmaceutical solutes are mostly non-volatile solids with strong internal bonds. They rarely escape the surface. Therefore, the total vapor pressure of the mixture comes almost entirely from the evaporation and condensation of the liquid solvent. Measuring that vapor pressure provides a baseline thermodynamic indicator of how eager a solution is to change its physical state. If a drug is going to remain stable in storage, we need to know exactly how much pressure its solvent will exert. To model this behavior, we use a theoretical baseline called the ideal solution. In this model, we assume all intermolecular forces, solvent to solvent, solute to solvent, and solute to solute, are perfectly equal. If all forces are equal, the total vapor pressure is simply the sum of its parts. This gives us Raoult's law, which states that a component's partial vapor pressure is equal to its vapor pressure in a pure state multiplied by its mole fraction in the solution. In this ideal state, physical behavior is determined entirely by the relative number of molecules competing at the surface. This chart shows an ideal solution on the left, where behavior matches the mole fraction perfectly. But real solutions, shown on the right, have unequal intermolecular forces. We have to replace the simple mole fraction with a new measurement, thermodynamic activity. If the solute and solvent have a weak affinity for each other, they escape the surface easily, creating a positive deviation with higher vapor pressure. If they have a strong mutual affinity, they hold each other in the liquid, causing a negative deviation. Pharmaceutical mixtures are almost always non-ideal. Calculating these exact thermodynamic deviations is how scientists accurately predict a drug's behavior inside a complex liquid formulation. When a solute dissolves, it often dissociates into separate ions. This occurs if the solvent has a high enough dielectric constant, like water, to pull oppositely charged ions apart. Solutes that do this are called electrolytes. Water itself naturally dissociates into hydrogen and hydroxyl ions. Under the Lowry-Bronsted theory, an acid is defined as any substance that donates a proton, a hydrogen ion, into that water. Because hydrogen ion concentrations span an enormous range, we compress them using a negative logarithm. This gives us pH, a tight mathematical scale running from 1 to 14. For oral drugs, this scale maps directly onto the gastrointestinal tract. A swallowed pill travels from the highly acidic environment of the stomach, where the pH can drop to 1, into the increasingly alkaline conditions of the small intestine. This shifting physiological environment makes pH the primary gatekeeper of pharmacology. The local acidity dictates where and when a drug becomes soluble enough to enter the bloodstream. To track how a drug responds to this changing pH, we measure its acid dissociation constant, or Ka. This constant tracks the equilibrium between unionized molecules and ionized species in weak acids and bases. Taking the negative logarithm of the acid dissociation constant yields the Henderson-Hasselbalch equation. It links the body's pH, the drug's pKa, and the ionization ratio. A strict rule emerges. When environmental pH equals the drug's pKa, it is exactly 50% ionized. This chart links pH to solubility. Weak acids maximize solubility at high pH, weak bases at low pH. Aspirin, pKa 3.5, stays unionized in the stomach. Imidapyrin, a weak base, is highly ionized there, shifting to unionized in the intestine. Unionized drugs are much more easily absorbed across biological membranes. By strategically choosing a drug's pKa, pharmaceutical scientists can explicitly program whether a formulation absorbs immediately in the stomach or delays until it reaches the intestine. Because a drug's ionization state is so sensitive, the formulation must defend itself against unwanted pH changes. This is achieved using a buffer solution, typically a mixture of a weak acid and its salt. When a small amount of external acid or alkali is introduced, the buffer neutralizes it. The presence of common ions from the salt suppresses the further dissociation of the weak acid, holding the pH steady. We measure this defensive strength using buffer capacity. This tracks exactly how many moles of strong acid or base the system can absorb before the overall pH shifts by a single unit. Maximum buffer capacity is reached when the ratio of acid to salt in the mixture is exactly 1:1. Returning to our earlier equation, this happens when the solution's pH equals the acid's pKa. Buffers act as biological armor. They protect sensitive drug molecules from degrading while sitting on a pharmacy shelf, and they keep the formulation stable the moment it mixes with fluids inside the patient. Beyond ionization, solutions possess physical characteristics that depend entirely on the total number of particles present, regardless of what chemical those particles happen to be. We call these colligative properties. The most clinically critical of these is osmotic pressure. When a dilute solution and a concentrated solution are separated by a semi-permeable membrane, solvent molecules spontaneously diffuse across to dilute the concentrated side. This is osmosis. The external force required to stop this flow is the osmotic pressure. For dilute solutions, we calculate this using the Van't Hoff equation. Notice the correction factor I. If the solute is an electrolyte, it breaks into multiple particles, directly multiplying the overall osmotic pressure. To quantify these active particles, we measure either osmolality, which counts osmoles per kilogram of solvent, or osmolarity, which counts osmoles per liter of solution. If two solutions have equal osmotic pressure across a perfect theoretical membrane, they are isoosmotic. But if they maintain that equilibrium across a real biological membrane, they are isotonic. Calculating exact isotonicity is a mandatory safety requirement for intravenous fluids. Injecting a severely hypertonic or hypotonic solution into the bloodstream will cause catastrophic damage to human cells. Once a drug is in the body, its molecules must physically move to their target. This spontaneous transference down a concentration gradient is called diffusion, governed by Fick's first law. To understand how molecules travel through a liquid, we look to the lattice theory. It proposes that liquid solvents form quasi-crystalline networks filled with empty spaces, or holes. Diffusion occurs when a solute molecule acquires enough kinetic energy to break its bonds and jump into an adjacent hole. We quantify this movement with the diffusion coefficient. It is calculated from the average distance of that molecular jump, multiplied by the frequency of the jumps. The Stokes-Einstein equation scales this up, showing how macroscopic forces impact that microscopic jumping. It defines the diffusion coefficient using the liquid's viscosity and the spherical radius of the solute particle. Because viscosity and radius sit in the denominator, the relationship is strictly inverse. The jump frequency and overall diffusion rate will predictably increase as the liquid's viscosity decreases, or as the particle size shrinks. From the initial vapor pressure inside a sealed vial, to controlling ionization in the stomach, to the final diffusion of a molecule into a target cell. These physicochemical laws provide the ultimate blueprint for all pharmaceutical design.